Hi, welcome to the Signal Pad. In this episode, we're going to convert a really old, obsolete instrument into something that I can use around the lab for my experiments as well as for instrument reviews. Now, I typically don't work on really old instruments. There are some really talented people on YouTube who take apart really old radios and fix them and tune them, like Mr. Carlson's lab, for instance. The reason I have this one is because it's a very unique use case that I want to apply it for. So let me first tell you what this is. This is an HP8445B. It's an automatic preselector. In the old days, when spectrum analyzers did not have their own preselector, you'd have to buy this box and put it in the front, and then you would basically put your signal into this and take the output of this and connect that to the spectrum analyzer. So what does this do anyway? Well, a preselector is nothing more than an electronically tunable filter. So this thing can be tuned anywhere from DC all the way to 18 gigahertz, and it's a bandpass filter. Now, spectrum analyzers use multiple conversions in a row. And I've talked about that in details in various repairs that we've done. Now, these conversions are all non-image reject, meaning that because you don't know where your image is and because you don't know which harmonic of the LO you're using, every frequency around the broadband signal can be converted into the same IF. And that would be a mess because you don't even know what you're looking for. So the best way to solve that is to say, I'm going to put a bandpass filter in front of my signal. As I sweep my spectrum analyzer, I'm going to sweep the filter with it. And I'm only going to look at the frequency that the filter is tuned. And everything else outside will be completely rejected. So I won't have no confusion about what signal I'm looking at. Now, there are some disadvantages to preselectors. They have loss, so they reduce the dynamic range of the spectrum analyzer. And almost every modern spectrum analyzer has one of these built in. In some rare cases, there are also software preselectors where you do many measurements and you dither the LO, and looking at how the image moves around, you can judge where the signal you're looking for is. That's a whole other story. So if you look here, each of these actually comes with its own little label that tells you what the insertion loss of this particular unit is across frequency. So you can see up to 2 gigahertz, it doesn't use a YIG filter. It actually uses a low-pass filter. And then somewhere around there it switches, and then from 2 gigahertz to 18 gigahertz, you have an insertion loss of somewhere between 6 to 9 dB. So that's a lot. You're losing a lot of signal over this. But of course, that's a small price to pay for you to be able to know what it is that you're even measuring. So why do I need this? I mean, all the spectrum analyzers I have in the lab definitely have preselectors built into them, and this is essentially obsolete. The reason I want it is because I can use this to create really pure tones. So if I have a synthesizer, and let's say the synthesizer is tuned to 4 gigahertz, and I don't want to have any harmonics. I don't want to have 8, I don't want to have 12 gigahertz, which are inherently generated by the synthesizers. This can filter them and give me a super clean tone at the frequency I'm looking for, and that would help me characterize other instruments because I know exactly the signal I'm giving them. And we're going to do an experiment with that, and I'll show you how important that is. I've done that in the past, but I've done it using these. These are just bandpass mechanically tunable filters, and you can see this is a cavity filter one, and it goes from 1.5 gigahertz all the way to 3 gigahertz. So it's only a factor of 2. But of course, the quality factor of this filter is quite a bit higher than a YIG one because it's purely passive. But this one is a YIG-tuned one, so it has quite a bit more insertion loss. But at the same time, it covers a frequency a factor of 9, whereas only a factor of 2 in here. So at the low band, of course, I have no YIG, so I have some ideas on how to change that and improve that as well. There's a couple of other problems with this. First is that this one does not have the option that allows you to manually adjust the frequency yourself. These knobs are all missing, so we're going to have to add that ourselves. This is only controllable with a port at the back with an analog voltage. So let's take a look at an example. So here I have the HP83752B. This is a 20 gigahertz synthesizer. Right now it's set to 2.2 gigahertz and a 4 dBm output power. And I'm connecting that directly to the oscilloscope right over here. This is connected to the Keysight MSOS. And we want to take a close look at the harmonics. So here's our signal. You can see it's about full scale, almost full scale at 100 millivolt per division. And here we have our fundamental 2.2 gigahertz. Second and third harmonics are there too. The third harmonics is the largest, and it's about minus 40 dBc or so roughly from the fundamental. The problem is that I don't know if these harmonics are generated by the scope or by the synthesizer that is connected to the scope. And you can't just get rid of them because you don't know the relative contributions of each of the instruments. So if I want to calculate the effective number of bits of this unit, the only way I can do it is to make sure that the tone that I put in is as clean as possible. So if I have a bandpass filter around it, these harmonics will be suppressed from the synthesizer, and then if they're still here, I will know how much of it is coming from the scope itself. And that's why I need an instrument like that. And that's just one example. This applies to any broadband front end that you want to characterize and find out its contribution to THD. And as I said, this does not get rid of the phase noise, but that's not what we're looking for here anyway. So let's go back now, take a look inside the YIG filter and see what it looks like. All right, let's take a look inside this. So I think I have to slide this. There we go. And yeah, it looks nice. It's mostly empty. That's not surprising because the dimensions of this chassis is set with the dimension of the spectrum analyzer this is supposed to sit on. And it doesn't have all the options installed. At the back here, this connector J4, that's the BNC input. This is 1 volts per gigahertz. So for every 1 additional volt, the filter would shift by 1 gigahertz. So we can use this to tune the filter. The problem is that we cannot enable the low pass directly from here. So we have to do some hacking in order to enable that feature, of course. And we have to override that from the inside. I want to put everything on the inside of the instrument so we don't have to have anything else connected to it. We got a couple of power supply control voltages here and everything that drives the YIG. Now if I follow the input, I believe here is the input. The input goes over here and goes into a relay. And this is the relay that switches between the YIG and the low pass filter. So on one side, we have this guy coming out here, going down into this low pass filter, and then back into another switch, and then back into the output. So we need 2 switches at the input and the output, of course, to switch between the 2 paths. From the YIG path, it comes out, goes over here, goes into the YIG filter, goes back into the other switch and back out again. So really straightforward. The YIG control here, the heater and the tuning of the YIG is all done through these cables. The relays are controlled in conjunction. They're all tied together, so that makes sense because they will always have to be in the same state. Transformer there, fan there, fairly big fan actually, and yeah, pretty straightforward. Some of these transistors will have to be controlling this guy, and some of them, particularly the ones probably with the heat sinks, are controlling this. This is most likely the power supply board. Yeah, looks good. The schematic of this is available, so we're going to use that to basically make our modifications. So what do we want to do? First, we want to install something in the front to be able to adjust the voltage that goes into this directly from the front panel. So we can basically tune the frequency we want. I also want to add a display to this that shows how many volts are present here. And since it's an easy conversion, just 1 volt per gigahertz, we can then estimate the standard frequency from that. That should make things quite a bit easier. So to get the upgrade started, I made some modifications to the front panel and added some features I was looking for. The very first thing I did was I removed that label that showed the loss of the front end. We don't really need that so much. It doesn't serve much purpose here. We just want to make sure that we can track the frequency. So instead I did a little 3D printed part here and I put a multimeter in there. And this little multimeter is going to tell us what the sweep voltage is. And since the slope is known, 1 gigahertz per volt, we can then find out what the standard frequency is. So this is going to be our readout, and this is the equation to calculate it. Really straightforward. Now we need a way of adjusting the frequency. So I have a 10-turn potentiometer here that's going to help us adjust the frequency when we're in the YIG mode. I also have a switch here that we can switch between the low band and the high band. So the low pass filter and the YIG filter, then we can switch back and forth, of course, and that's about 2 gigahertz. But I really wanted to have bandpass response also in the low band, not just the low pass response. So I made a link here, and this link is just basically a through, but I can remove the link and connect it to one of my adjustable filters, the ones that I showed earlier, the mechanical ones. And that way I can also have a low bandpass filter as well, and that would cover everything roughly from DC all the way to about 20 gigahertz or so, maybe 18 gigahertz or so. I also changed the connectors that were type N to these other type of connectors. These are type K, and ironically enough, these connectors are now much more expensive than the instrument itself. So it looks nice. I think it's a good start, and the back of it is all these are just now ready to be wired up. We can see that we have access now to the back of the SMAs. Here's the type K connectors, our potentiometer, our switch here to switch the low band and the high band, and here's our multimeter. Now this needs its own 5 volt supply, so we're going to have to make some modifications to give this guy a 5 volt supply to be able to make that measurement. But also there are other things we need to worry. So how do I connect these switches? How do we modify the circuit? And I want to do this with absolute minimum changes to the instrument as possible. So now I think we should go back and examine the block diagram and the circuitry of what's in there and find out what's the quickest way to add these features. So let's take a look at the service manual of this instrument, which is readily available, but because it is so old, only a scanned version of it is available, and it's really oddly arranged with bits and pieces of information all over the place showing different options all at the same time. So it's really not that easy to read, but it's tons of details. So if you spend time on it, you can figure it out. Now, luckily, we're not really trying to do much. All we want to do is to figure out what is the easiest way to control the relays so that we can switch between the low band and the high band, and how can we apply a voltage directly to the tune that I can control with the potentiometer from the front panel. And since I've installed a multimeter in the front, we also need to steal some DC power to be able to power that separately. So let's look at the relays first, because those are the easiest thing to find. Here you go. So there it is. You can see one relay over here, one relay over here, and one relay over here. And the reason why I chose these relays is because and one relay over here. These are the two switches that basically switch between the low pass filter and the YIG filter. That's exactly what we want. And if you look at the way they're controlled, they're basically tied to each other. And you either have to apply a positive polarity on it or a negative polarity, and that relay will just switch mechanically from one to the other. That means that it's really easy to drive. You only need to worry about these two wires. And you can do that very simply with an H bridge, which is what they've built here. You can see the combination of these 4 transistors over here basically drive these relays. So there's a PNP and an NPN in an H-bridge configuration. You can see the 2 outputs, and the inputs of those are controlled with 2 other devices. You can see there's 2 other PNPs here that drive them, and then there's another NPN device here. But luckily, it seems to be that there is a dedicated NPN device here that it has an available port, and that port is conveniently called relay. So by playing on the voltage of this, you can switch this H bridge from one mode to the other. So normally if it's pulled to ground, it will be in its default state. But if you pull it high to 19.5 volts, which is the power supply used inside the instrument, it will switch to the other side. So all we need to do is to find this and tie it to 19.5 if you want to switch to low pass. And that can be done with just a basic switch, which is what I have on the front panel. So that makes things really easy. And what about controlling the voltage? Well, there is an option too here that if the instrument had, would actually have a front panel control, and it had a fine and a coarse tune, but I don't want to get into so much trouble there. I just want to use the basic circuitry that is there without modifying anything. So if I go down over here, I can see that this is a remote panel BNC input, and that input can control the voltage at 1 gigahertz per volt, which is what we want to control. So I can just tap onto this and steal that voltage and create a voltage divider from a 19.5 volt, very similar to how they were doing it with the potentiometer, but I'm going to only use one potentiometer and drive that directly. So basically with my single potentiometer taking this voltage, I can simply do the tuning with it. That makes things easy. And I can then monitor the voltage that I'm applying here with the voltmeter, find out what that is, and then multiply it by 1 gigahertz per volt and get my center frequency. So all of that sounds pretty easy. So we can go ahead back to the instrument and see what modifications I've made to make these available and see what it looks like. So here's the instrument with all the modifications, and things are kept as simple as possible. So let's look at the bypass mode that I installed. The bypass mode is simply going to allow us to put something in line or in series right after the low pass filter. So the output of the low pass filter is taken out into the front, and then there's the loop back, and then comes back over here and goes back into the relay, which then goes to the front panel again. So this allows me to add, for example, a tunable mechanical low band pass filter as well to right after the low pass filter. So we get that functionality for the low band too. Now in terms of all the electronics, really kept as simple as possible. This connector over here already had a nice little actual interface connector built into it, so that makes things really easy. I just soldered the wires directly to it, and here I can take 19.5 volts, the ground signal, as well as the relay control directly from here. Send those out to a switch that's in the front. At the same time, power a potentiometer that's going to give us the analog tunable voltage. Bring that voltage back, share it with the voltmeter in the front, at the same time pass it back into the board, which then is connected exactly the same pin that the front end BNC is connected. There's a little nice daughter board here, which is like a distribution board that they're using. Now at the same time, ironically enough, I actually didn't have a 5 volt voltage regulator, but I did have a DC-DC buck converter, so I used that to create 5 volts. This is not ideal because this has some switching noise. So to avoid some back EMF from that, underneath this shrink tube here, there's actually a 150 ohm resistor that's in series. Since this thing burns basically no power at all, that's going to create a nice filter in conjunction with the input capacitor here and filter all the noise. And all the power supply controls that I need are taken before the resistor. So this is just a low pass, eliminating any kind of spikes from the signal, from the entire signal path there, no pun intended. And that's it. The rest is really nothing else. So everything else is kept unchanged. So now it's time to test it. I'm excited to see how it performs. So let's give this a try and see how well it works. Here I have 2 phase stable Gore cables directly connected to the inputs, and at the far background you can see a network analyzer running from DC to 20 gigahertz. Right now everything's turned off, so you cannot see anything, and this can be selected between the high band and the low band. So let's turn it on and see what happens. Let's put it into low band here, and there we go. Yeah, the fan is pretty loud. And in fact, if you look in the background, you kind of can see the low pass response happening there. So that's quite nice. So it's indeed working. We're going to take a look at the screen in details. And right now this is off because we're in the low band mode, so there's nothing being displayed there. But I can switch to the high band, and immediately I will get a voltage here, and that voltage is going to be our center frequency if you multiply it by a gigahertz per volt. And indeed you can see a little bandpass response there on the screen. And if I go ahead and adjust that, you can see this voltage is changing, and if you look in the background, the center frequency is moving. So it's working really nicely, so I'm quite happy about that. But we should take a close look at that and see what the characteristic of this filter actually is. I'm going to go back to low band here. Now I'm going to go and take a look there, but I don't want to just have a low pass response. I want to have a band pass response even at the low frequency. So I'm going to put a band pass filter instead of this link once we take a look at it. Let's zoom onto the screen. And here is the low pass response. Look at that. This is beautiful. Look at that drop. That is a massive drop in such a small frequency range. This must be, I think it's an 8-pole filter. It's fantastic. So we have fairly nice flat response here and just cuts everything out. It does have one mode that kicks in at later frequencies here and another one at the very end close to 20 gigahertz. But of course this is probably not an issue for when this instrument was being used, and I verified this is indeed from the low pass filter. So once I add my own band pass filter, this will certainly go away, and we can try that out. So yeah, it looks nice. You can see it goes just below 2 gigahertz, exactly what we wanted. I'm going to turn on into high band mode, and here's the high band mode. So right now you can see the center frequency is right here. It's about 4.8 gigahertz, and amazingly on the front panel, unfortunately you can't see it, it says 4.8 volts. So it's really nice, and I can do some fine-tune adjusting as well, but really I can move this around like so very nicely all the way to the end and all the way back. And of course it's very fast because it's a YIG filter. You can see another tiny mode kicking in here, so it does have certainly something that comes back up. And now this is not related to this tone over here. They're not actually having to do with each other, because I can move this out. You can see that this is nothing to do with it. This low pass response is purely from that low pass filter that's in the circuit. So let me go ahead and remove the link and put my own bandpass filter so we can get a nice tunable response at the input as well. And here's the measurement, and check it out. Now I have a tunable bandpass filter at the low frequencies as well. So here is 1 gigahertz. I can go all the way here to 2 gigahertz, and I can put any bandpass filter I want. And as soon as you hit 2 gigahertz, we can switch to the high band. Here's the high band, and we can continue from there all the way to the end, as you can see. So very nice. So we have a full band control with a very, very high quality bandpass filter through the entire band. So now what can we do with this? Well, the very first thing is to show how much of an improvement we get using this actually with the spectrum analyzer. And the spectrum analyzer is booting, and you probably heard the attenuators as it was going through the boot up sequence. Now there is something to consider here, especially when I'm using a YIG filter. If you look at the YIG filter, it has quite a bit of insertion loss. So over here, you know, we're looking at about 8 dB of loss here, which is a lot. But of course, that means that I have to push the source higher in order to match the same output power. So the source becomes more nonlinear, so you're kind of undoing what you want to do. But because the rejection of the filter is so huge, the overall gain is going to still be there. And we're going to see that in measurement. Well, let's jump and try that. So for the first measurement, I'm directly connecting the synthesizer right over here to the spectrum analyzer with nothing in between. So what we will measure is the true THD of this instrument. Let's take a look. So here's the raw source, and you can see here's the fundamental 2.2 gigahertz, and I'm going to keep the amplitude at 0 dBm, so we have a direct comparison. We're measuring the power directly at the input of this instrument, not the power at the output of the synthesizer. So here's our second harmonic. So you can see that the THD is about, you know, minus 44 dB, which is not that great, especially if you want to characterize, let's say, a high performance analog to digital converter. Third harmonic, fourth harmonic are also present. They're quite a bit smaller, so they don't contribute much to THD, but you can still see them. So now let's repeat the experiment where we take the output first into the bandpass filter and then into the spectrum analyzer. And here's the modified setup, the output to our modified YIG filter and back to the spectrum analyzer. Now let's see what happens. And as you can see, the difference is astonishing. You basically don't see any of the harmonics anymore. Remember, this is at the same output power, so the source is being pushed even higher, but you still see absolutely nothing because the rejection of the filter is so enormous. I can change the bandwidth here even more and see if we can catch it. There it is. It's all the way down here. Is our second harmonic. So now our THD, you know, is about 75 dB, minus 75 dB. It's a big, big difference. So now that we have this, we can go ahead and try it on the oscilloscope. So I have about 3 oscilloscopes, or maybe 4 oscilloscopes here that go up to above 6 gigahertz. So we can try it out and see what kind of response we get from either one of them. So here's the response from the Keysight MSO-S series, and we can see that here's our fundamental is at minus 1 dBm, so it's 600 millivolt peak to peak on 100 millivolt per division scale, and you can see the third harmonic is sitting around minus 45. So that's from the scope, that's not from the source anymore. So this allows me to calculate the THD, the SNDR, the SQNDR, and every other characterization of the front end directly using that instrument. This is the main reason why I built it, because I wanted to characterize high-end ADCs like this and high-end oscilloscopes like this. So that's what the Keysight does. Let's try something else. And here's the result on the RTO 2064. This instrument does not go to 8 gigahertz, so we're not going to be able to see the third harmonic as well, but we can see the second harmonic. So here's the fundamental at exactly the same amplitude, and you can see the second harmonic right over here. It's also at around minus 45 dBc, which is good. This tone that you see here is actually a bit larger. This is the time interleaving tone that has to do with misalignments between time interleaved ADCs. It's at 5 gigahertz, most likely 1/4 of the sampling rate. And this sometimes can go away if you do calibration of the time interleaved ADCs. And I think the new ADCs that Roden Shorts has made are actually quite a bit better than this also. But anyway, the third harmonic is not there, but you can see the exact same result. Just to show you that tone is not from the instrument, it's not from the synthesizer. I can turn the synthesizer off, and you can see that we still see exactly that tone present because that's just from internally generated. So I think I'm going to go ahead and measure the rest of the instruments and make it a table and make it available on the website. But I think the main purpose of this instrument is now clear, and why I made it is going to show up a lot of other videos on high-end instrument characterization. But now for the exciting part, I'm going to give away one more of these Keysight DSO-X 1102Gs. I think this is the third one that I'm giving away, or the fourth one, I'm not sure. But yeah, so if you want one of these, leave a comment in the video. Of course, all my Patreon supporters are already entered, and they get a 3-to-1 odds. So if you leave a comment and you're a Patreon, I'm going to enter your name 3 times into the draw so that you have a much higher chance of hopefully winning one of these things. And yeah, there's going to be more of these giveaways. I hope you enjoy them. I want to thank all the viewers and all the Patreon supporters. As you know, none of my content is behind a paywall. Everything that you see is exactly available to everyone, and the supporters support that knowing that they're helping the community. I hope you enjoyed this video. I'll see you next time.